we'll start bipolar junction transistor. The short form is BJT. It says it has two polarities, majority and minority carriers. Junction is there, two junctions are there. Transistor is a word developed from transfer of resistance. So it works on the principle of transfer of resistance. That is the meaning of transistor. The topics I have taken are divided in this one: manufacture of BJT and current components, early effect and BJT characteristics, Eversmole model and testing region. The fourth and the last one is transistor as a switch. These are the four topics I have divided in this BJT. Each one we will do separately. First one, manufacture of BJT. It's a 3-layer active device consisting of two PN junctions connected back to back. And it works on the principle of majority and minority, so it is called the word bipolar. Bipolar means two polarities. You observe here how PNP is working. This is PN, this is another PN. So back to back connected PNP. This is NP, this is NP. So back to back connected NPN. So PNP transistor, NPN transistor. So back to back connection of two diodes is treated as a transistor, but never work as transistor, and hence a separate manufacturing is required. What I mean there? Why do I say that? Because if you see this PNP back to back connection, that doesn't talk about doping, that doesn't talk about the sizes there. So if the sizes to be different and the doping to be different, the back to back cannot work as a transistor. So we need a separate manufacture. That's why we will see the manufacturing process. Physical behavior of BJT. Emitter is heavily doped P+, base is lightly doped N-, collector is moderately doped, therefore it is P. Heavy doping means 1:10 power 3, live doping is 1:10 power 10, moderate doping is 1:10 power 6. And we need to understand why the doping is like that and why the sizes are like that. That's called manufacturing. Let's go one by one. Emitter. It emits carriers. It's heavily doped to emit more carriers. The size is moderate to maintain that doping, and also because it need not dissipate temperature. Because collector really dissipate temperature, but emitter will not dissipate temperature, so it need not be large. Anything that is dissipating temperature should be large. Second, base. I said this is basis for amplification. That's why it's called base, a common terminal. It's lightly doped to reduce recombinations within the base, so as to increase collector current. Suppose if recombinations are decreased, collector current will increase. It is small in size to reduce base transit time. What is base transit time? The time taken by the carriers to cross the base and enter into collector. That's what it is, base transit time. Take an example, I took it. Suppose 100% emitter current is coming here. Because doping of the base is less, only 2 to 5% is here. Remaining 95 to 98% is here. Therefore, based on this, I have defined current gains. Common base, common emitter, common collector. Suppose base is common, that will not come. So IC by IE. Emitter common, emitter current will not come. IC by IB. Collector current, emitter by IB. Just for example, these are not the constant values or the fixed values. They can change. Just for example, I took this. So IC is 95 to 98 by 100, 0.95 to 98. That's the reason why alpha is less than 1. Beta 95 to 98, 2 to 5, 19 to 49. And gamma 100 by 2 to 5, 20 to 50. By looking at this, you can say one thing. Alpha, beta, gammas are not fixed values, but they are a range of values. And depending on the biasing conditions, the exact value will be known to us. Depending on the biasing condition, currents will be decided. When the currents are decided, you can say alpha, beta, gammas are there. Now, IE is equal to IC plus IB. If you substitute that, you can convert everything. All currents we can convert. Alpha is beta by 1 plus beta. Beta is alpha by 1 minus alpha. Gamma is 1 plus beta is equal to 1 by 1 minus alpha. These are the DC current gains. So DC current gains has a direct impact from what you call base doping and base width. Let me take you to the third terminal. Collector collects carriers. It's moderately doped to avoid collisions in the collector. For example, if you take already more and you are sure that current is coming from emitter, once they come from emitter, they will take more. They become more and collisions will become more. And ultimately, the amount of current is decreased. It is large in size to dissipate temperature collected at the collector. So these are the two reasons why doping and size is there. Now back-to-back connection of a transistor can be treated as transistor. Back-to-back connection of two diodes can be treated as transistor, but never work as a transistor because doping is different, sizes are different, and hence we need to manufacture separately. This is what I mean by sizes, manufacturing. And if you see energy band diagram, roughly, this is not the accurate one, but an idea I wanted to give. This is conduction band, valency band, emitter, base, collector. These are going from here. Okay. So when the electron is going from here to here and then falling down, when anything is falling down, there will be temperature developed. So IC gives temperature, and that temperature affects IC naught, and that once again affects IC. So this is called a cumulative effect, and that's called thermal runaway. Okay. This is how we can say how the manufacturing is done. That's called manufacturing is done. The second we are going to the topic is current components. Look at your P plus N P. If you look at this, first thing I need to tell you is they seems to be equal. They are not equal as we studied. The sizes are different. But for the convenience, I have drawn like this. The actuality is emitter is medium, base is small, collector is large. Now when I look at this, P is given to P is a forward bias. P is given to negative, reverse bias. So this is called forward bias, reverse bias. VEB, because base is common. So please understand here, this negative sign has come because base is grounded. Minus, plus, minus, plus. So please remember, this is minus because ground, therefore it is plus. This is minus because of ground, this is plus. And this positive nothing to do with this. So this is called terminal voltage, this is called supply voltage. Terminal supply. Terminal supply, okay? Nice. Now, if you say VE is a majority carriers, what are majority here? Electrons, holes in emitter, electrons in base. So they will be conducting here. If you see VCC is a reverse bias, and then you can say that minority carriers. What is minority? Electrons in collector, holes in base. So ultimately, at the input side, emitter junction, two majority carriers, at the output side, two minority carriers. So how is this carriers all the current components and contributing the overall current? We need to see that. That's called current components. Okay. Now let me take you to one by one. Emitter base junction. Forward bias majority carriers, as I already told you. What are the majority carriers? Holes from emitter goes to collector and also to base, and because there is no attraction but they are being pushed there. Let me tell you. Let me show you what it is. Look at here. Here is the carriers. Holes are here. They are pushed by this positive, attracted by negative. But where is the component out of this current? Something comes here to the base. It is neutral. No attraction, no opposition, but they are really going in this way. Why? Because these holes are pushed by that. So ultimately, holes from emitter going to base, then collector. Electrons from here will not be attracted by this, it will have only attraction by emitter. So hole have two components, electron has only one component. Look at here. Hole have one component and two components, whereas electron has only one component. When hole is going, we are given the same direction, but when electron is going, we have given opposite direction. Okay, that's the meaning. Why opposite? Doesn't here. All internal currents are conventional current, same as holes and opposite to electrons. So holes are going this way, electrons are going this way. So when we want to take everything as a whole current, you take opposite here, electrons. So at the outset, I want to say emitter current is these two currents, IPE, INE. Now let me take you to the next junction. Collector base junction, reverse bias. Reverse bias means what? In this P, electrons are coming. Electrons are going this way. From P, electrons are going into the base. From N, holes are going. Holes cannot go this side, they only go here. You see that? Holes from base go to collector but not emitter. They don't go to emitter. But electrons from collector goes to emitter but also to the base. But what happened after? They get recombined in emitter. So recombination is taking place in emitter. So ultimately you have two components here. One is IPCO, INCO. If you add these two components, you will have ICO is minus of IPCO plus INCO. These two currents get added. So this is minority current. What is overall current? Apply KCL at collector. IC entering, IPC entering plus ICO is equal to 0. IC is minus of IPC plus ICO. What is IPC? Collector current. There is one concept called IPC is approximately IC. Therefore, IC by V is alpha. Now, what is IPC? Alpha times of IE. Look at here. IC is equal to minus alpha times of IE plus ICO. Then IC, IB plus IE. You know all currents are entering in the transistor. We have assumed only here. Look at here. This current is entering, this current is entering, this current. So all the three currents are entering. So we have taken it as added. Therefore, IE is equal to minus IB plus IC. If you substitute this, minus of minus become plus IB plus alpha plus IC naught. If you take IC common, 1 minus alpha, alpha IB and all that. So IC is equal to IC by alpha by 1 minus alpha into IB, 1 by 1 minus alpha into IC naught. As our conversion says, alpha by 1 minus alpha is beta, 1 by 1 minus alpha is gamma, that is nothing but 1 plus beta. Therefore, IC is equal to beta times of IB plus 1 plus beta times of IC naught. And if you really neglect this minority current, IC is equal to beta times of IB. Therefore, collector has a driving capacity. It can drive any amount of current. To make transistor analysis as two-port analysis, we always take both currents entering. Both currents entering, normally in a transistor we should say collector current is leaving. But purposefully we took both currents entering to tell you one thing: transistor analysis is taken as two-port analysis. But only one thing, if IE is leaving, it is added, IC plus IB. If IE is entering, minus IC plus IB. So these are the currents that we have. Okay. Common base. IC by IE, IC by IC plus IB, this is the conversion. Base is common, output by input. Common emitter, IC by IB, this is the conversion possible. But when you look at this, you have 180 phase shift. You know why 180 phase shift? This is II. I0 is opposite. II is entering, I0 is leaving generally. So these two are opposite. That's why 180 phase shift. Common collector. So look at here, common collector. This is IB, IE. So IE by IB is the definition. That's 1 plus beta. It's around 1 plus 19 is 20. 1 plus 49 is 50. So it varies from 20 to 50. Let's go to illustrative examples. When I say illustrative, I mean we are still studying concept, but not in the topic way, but in the illustrative problems. They will really help us to make the subject better. Then we'll go to work out examples. The first question: why collector is larger? The answer: you look at here, as I mentioned, there is a temperature developed. When temperature developed, what should happen? You have to make collector as larger. IC is beta times of IB, 1 plus beta times of IC naught. As temperature increase, IC naught increase. As IC naught increase, IC increase. Therefore, when IC increase, temperature increase. When temperature increase, IC naught increase. Once again, IC naught will increase. Therefore, temperature is increasing like anything. Such a process is called thermal runaway. So ultimately, collector size has to be larger. Second, what is thermal runaway? How to eliminate it? What is thermal runaway? How to eliminate it? As already mentioned, it is a process. Thermal runaway is the cumulative process of IC, TJ, IC naught, and it is avoided by taking VCE less than or equal to VCC by 2. So remember that. If you really want to make temperature 0, there is no way except saying IC 0. If IC 0, it is useless. That means we need IC, we also need temperature is there. So collector current and temperature are inseparable things. Third question: what is base transit time? What is base transit time? It's a time taken by the carriers to cross the base and enter into collector. So we need to see that they go very fast and go into the collector. So that's why we normally make base as small to increase fast or to decrease the time. That's a base transit time. How to increase output current IC? I mean, what are the things, what are the parameters and factors on increasing IC? Look at here. Collector current increases if emitter doping increase, first point. Second, if base doping is decreased. If base doping is decreased, what's happening? The recombinant is decreasing, collector current is increasing. Second. Third point, base width also should be decreased. Next, collector doping is moderate. When the collector doping is moderate, what are the carriers coming from emitter through base? They don't collide. That's why there is a safety way of learning. Current can increase. If all these things are not sufficient, if you have done all these things still you are not happy about the collector current, the last resort is non-uniform doping. When the uniform doping is there is no concentration gradient. If the non-uniform doping is there, concentration gradient is there, they easily move. Therefore, that is one of the last way to do it. So totally, I have given you 5 ways that you can increase collector current. One of the strongest point of BJT is output current is high. That's why it is still in the market and applications today. So that's a very serious matter, why and how the output current is high. In fact, why the output current should be high? The current should be high in order to drive any circuit. The more the output current, the more it can drive. Today it can drive even a big things. So such a powerful transistors we are making, in fact we call them as power transistors. Define current gains. As we already said, alpha, beta, gamma, they are the values. Alpha is far less than beta, less than gamma. Therefore, which one has the highest current gain? Common collector has highest current gain. That's why most of the time before we put the real load of an amplifier or a switch, we always put CC because it gives more current. And the current is more, that's why sometimes CC is called pass element. Because it's passing on this more amount of current there. Right? Then 6th question. What is alpha T? Alpha T means basically transport factor, but how is it defined? T for transport factor. Because we are transporting IPE to IPC. That's why I said whatever is giving at the emitter is going to something is going into collector, something is lost in the base, therefore how much is being transported? That's approximately equal to IC by IE. That's why alpha T is approximately alpha. Only once I am talking on this because of the fundamental class and the introduction class. Once I do it, later part I will never bring this concept called alpha T, but I will be just going with alpha there. With our relation we can show that alpha C, IPC is approximately alpha IE. This is what I have used in the current equation there. 7th question. What is the significance of BVCO? Breakdown voltage between collector and emitter with base open. They're asking what is the significance as such. Look at this. Voltage across collector is there. If base current is not 0, there is a drop here. If drop is there, how much voltage comes here? It is not VCC will not come here. If VCC is not coming here, there is no chance of breaking down because something is dropped here. But in the same way, if IB is equal to 0, open circuit here, and once IB is 0, IC equal to 0, when IC is 0, the total supply comes here, there is a chance of breakdown occur. Therefore, breakdown has a link with input current 0. Breakdown has a link with input current 0. And that's why people normally say, whenever they talk about breakdown, they always say input is open circuit. Open means 0 current. That's why I said, I have written a sentence there, breakdown is generally linked with open circuit input. Problem 8. The breakdown voltage of a transistor with its base open is BVCO, and that with emitter open BVCBO. Then what's the relation? BVCO is equal to both are equal, or CE is greater than CB, CB is greater than CE, and nowhere related. That's given in gate 95. 1 mark. Look at here the relationship. This is common emitter, this is common base, 1 by beta. And you know beta is large, 1 by large is a small quantity. Therefore, VCO is smaller than BVCO. And that's why the common base can bear large voltage than the common collector, common emitter. That means indirectly, even if the common emitter breaks, common base will not break. That's the meaning of it. Option is C. Ninth question. Asset A. Semiconductor devices like BJT have a maximum temperature operation beyond which they do not function. It is true. Every device has a temperature range and beyond which they don't work. Therefore, it is true. A is true. Eccentric p-type and n-type semiconductors behave as intrinsic semiconductor, that the temperature and effect of doping is lost. So, if you go on increasing temperature, the fermi goes on decreasing, therefore, and they come to intrinsic semiconductor. So, that's why there is a saying that I have already discussed in semiconductors by saying at extremely high temperature, eccentric semiconductor acts as intrinsic semiconductor. Therefore, that is also true. Now, the question is, are they linked or unlinked? Because asset and reason. This is IES question, ENT 2001. It's both are linked. Therefore, when the temperature is increasing, both statements are true. When the temperature is increasing, automatically eccentric semiconductor becomes intrinsic. Therefore, transistor also fails. That's why it's not only the semiconductor material has a temperature range, it is also the semiconductor devices have temperature range. 10th question. Asset A. In a transistor, thickness of the base region is kept as small as possible. It is true, because we discussed it already. By keeping the base thickness small, a large electric field is produced between the emitter and collector, which makes the transistor fast acting. There's no link actually. There's also a question given in the IES exam 2003. Option is C. That means A is true, reason is false. So these are the things, some questions I have selected or I have framed so that we can understand the concept well. That's why I named as illustrative concepts. So let me go to the next workout examples. So let's go to workout problems. This is for you actually, I am working for you. Right? This illustrated examples is my responsibility to illustrate the concept and see that you really understand. But when it comes to workout example, I am working for you. So work with me and then go to exercise problems, which I are going to put it in the question banks in website. Okay, let's go to workout problems. An emitter in bipolar junction is doped much more heavily than base as increases. Emitter efficiency, base transport factor, forward current gain, all the three above. If you look at base transport factor, beta IC by IB. Okay. Now you can say when IC, where IC the collector current, which is not the recombination in base. As IE increase, recombination is neglected. When recombination is neglected, what happens automatically? IC becomes approximately IE. That means whatever you are giving isn't going there, is simply going out. Therefore, beta increases to 1. Therefore, option is B. It's simply increasing beta. Question number 2. Which of the following statement is correct? He has given ABC statements we have to see there. ICBO is greater than ICO and does not depend on temperature. ICBO is greater than IC0 and doubles for every 10 degrees centigrade rise in temperature. ICBO is equal to ICO and doubles for every 10 degrees centigrade rise in temperature. ICEO is equal to IC0 and doubles for every 10 degrees centigrade rise in temperature. So what is this basically? The statement B is correct because ICBO is greater than ICO. Let me explain to you with supporting argument. From the equation ICO value times of IC0, ICO is slightly greater than ICO due to the some induced current flowing through the surface. Therefore, our option is B. You can see B here. Once again, I will show you. ICBO is greater than IC0. And IC0 changes for every. As IC0 changes for every degree centigrade, it is also ICBO also changes. So therefore, our option, you see, A and B are almost correct, but only thing is depends on temperature. That's why my final answer is B. I am leaving out to B. Problem 3. In a junction transistor, the collector cutoff current ICBO reduces considerably by doping the emitter with high level impurity, emitter with low level impurity, collector with high level impurity, collector with low level impurity. This is the question. In a junction transistor, the collector cutoff current ICBO reduces by doping what? Just now we have mentioned, if emitter is doping heavily, it emits more carriers and the large signal current. Therefore, what happens here? Alpha is IC minus ICBO by IE. If you look at that, it is indirectly becoming as IC is alpha times of IB plus ICO. Now, as ICBO, as alpha increases, ICBO decreases. When ICBO decreases, option becomes A. I'll show you what is A again. Emitter with high level of impurity. So that is how the option has become A. Question number 4. Assert. If we have two PNP and NPN transistors of identical construction, the NPN transistor have better frequency response characteristics compared to PNP transistor. Better. Why? This is a statement that is true. The diffusion constant of electron is higher than that of hole. So when the diffusion current is higher, constant is higher, automatically this becomes A. So when the diffusion constant is higher, automatically frequency response is better. You know, frequency response is actually linked with F tau that I will be discussing in high frequency concepts, but that is linked with diffusion constant also. So option is A. A means what? Both are true, and reason is the reason for assert. Problem 5. The graded base BJT exhibits better high frequency response characteristics as compared to their uniform based counterparts. You know what exactly I mean by the graded? Graded means non-uniform. There is a concentration gradient. So once again I am reading assert. The graded base exhibits high frequency response than uniform natural. Then reason, there exists a built-in electric field in the base region of a graded base which is absent in the case of uniform base current counterparts. And this ABCD we don't need to see, because in a certain reason we always know what it means by ABCD. Both are true, A is the reason for, R is the reason for A. Both are true, R is not the reason for A is true, R is false, A is false, R is true. Simple. So it's only the question is changing, it's not options changing. That's why somebody asked me, sir, if both are false, what happens? I said there would be no question like this. So when you look at this, our option is basically A, because uniform is, graded is always better compared to this. And when the uniformity is there, there is no field. When there is no field, is it? Let me read for you once again. There exists a built-in field in the base region of A which is absent. So because it is a uniform means it doesn't have any gradient. When there is no gradient, the current will be less there. That's why our option is A. Problem 6. If Alpha F and alpha R denotes the forward and inverted mode of current gains of BJT. Which one of the following is correct? Alpha forward, alpha reverse. Alpha forward, both are equal, lesser, greater, far greater. Our option is forward is always greater than reverse. Actually, this is indirect, it is very much used in Eber-Mol's model. Maybe we can discuss that when we come to Eber-Mol's model there. So, generally forward is greater than reverse. That's option D. Problem 7. The reverse bias breakdown of high-speed silicon transistor is due to, first of all, reverse bias, high speed means heavily doped. Then automatically, is it avalanche breakdown mechanism at both the junctions? No. Zener breakdown at both junctions? No. Zener breakdown mechanism at base collector junction. Zener breakdown mechanism at base emitter, because reverse bias is basically at base collector, because in a transistor input is forward and output is reverse. Therefore, my option is C there. Option is C. And you know one thing, 2 points you must be very clear. Reverse bias is at output junction, therefore base collector is correct. And the breakdown generally initiates with this Zener effect but dominates with avalanche effect. That I have been telling in the diodes there, particularly in special diodes, I was very clear about this concept. Zener initiates a breakdown process and avalanche enhances and takes it to the breakdown. 8th one. An increase in base recombination of BJT will increase. Suppose if the base is increased, what will happen? If the base recombination increase, the first of all, collector current will decrease. When the collector current decrease, automatically beta decrease. So which one will increase? Beta decrease, but he says increase, no? Breakdown voltage increase. Increase. The unity gain cutoff frequency, transconductance. This is a question asked in the exam. The breakdown voltage VCBO increases if base recombination BJT increases. Please understand, as I have been telling, if base recombination increases, base current increase. If base current increase, okay, he said an increase in the base recombination. When the base recombination increase, what is happening is IB is increasing. When base current is increasing, IC is decreasing. When IC is decreasing, what will happen? When IC is decreased, automatically the drop is increased, therefore the voltage at the VCE decrease there. So when the base current increase, okay, when an increase in the base current recombination of BJT will increase, you have so many things affected, but the breakdown voltage increases if the base recombination of BJT increase. So option is B. 9th question. Consider the following statements S1 and S2. Statement 1. The beta of a bipolar transistor reduces if the base width increases. If the base width increase, automatically collector current decrease. If collector current decrease, beta decrease. Step 2. Statement 2. The beta of a bipolar transistor increases if the doping concentration in the base is increased. If the doping concentration is increased, IC decrease, their beta cannot increase in that. So you see the true and false and true and false here. What we say is, if you look at here, IC by IB is this. If base width increases, recombination of base increases and beta decreases. Because its recombination is increasing, IC is decreasing, therefore beta, and hence alpha decreases. That's a different story. If beta in the base region increases, if doping in the base region increase, then recombination of base increases and beta decreases. So in both the cases, what's happening is beta is decreasing. But the question, what is it? Therefore, option is D. What is D? In first case, he said beta is decreasing. That's correct. In second case, he said beta increasing. That's why S1 is true, S2 is false. Because in both cases it's decreasing. See, one thing very important, all this question he wanted to know whether we know the manufacturing of BJT. When the base width increase, what happens? When the base width increase, IC decrease, therefore beta decrease. When the doping increase, IC decrease, beta decrease. So therefore beta decrease is a correct answer for both. And hence I say option is D. Last question. What is the most noticeable effect of small increase in a temperature in common emitter connected BJT? BJT is connected in common emitter configuration. When temperature is increasing, what is the most notable thing? Is it IC not increase? Output resistance, decrease in current gain, decrease in forward gain. This IES here. As you know, IC0 is bare times of IC0, where IC0 is approximate doubles for every 10 degrees centigrade in rise in temperature. Therefore, the most noticeable thing that's going to happen is in ICBO or ICO. What is the main difference between ICBO, ICO? ICO means the current actually crossing the junction. ICBO is a larger than ICO. That's why I've been telling ICBO is greater than IC0. Why and how that is increasing larger or how it's becoming larger? Because it's not only crossing through the junction, some currents are going through the surface of the transistor. They got added. And in the process, ICBO become larger than ICO. So whatever effect is there in IC0, the same effect is there in ICBO, therefore it increases. Therefore option is A. Because there will be effect on all, but most effect is available in IC0. That's about the lecture on the first one called manufacturing, current components, and then other related issues of the base emitter collector terminals, both in their doping and in their bits. With this, we introduce the topic called a transistor, and we go to the other topics later.